All right, so let's talk about capacitors in circuits. Behold the first circuit of the course, other than the one I showed in the FET demo earlier. So let's start to push this around. So here's a circuit full of 3 capacitors. They happen to be in parallel. All right, so this is a parallel circuit because stuff's in parallel. And there's 1 voltage in a parallel circuit. Every branch of this circuit has the same voltage, same electric potential. Just like the lights in this room. These 4 banks of light, they're all the same electric potential because they're configured in parallel, much like essentially the same way this is. All right? So 1 voltage, but depending on the capacitance, we could have different charges. So charge 1 would be capacitance 1 times this single voltage that we have. The charge on capacitor 2 would be its capacitance times the same voltage. And of course charge 3 would be capacitance 3 times this 1 singular voltage. So we have constant voltage in this. And the total charge would be the sum of all of the little charges. So in this case, that would be C1 voltage plus C2 voltage plus capacitance 3 and the voltage, which would be simply the sum of all the capacitances times that voltage. So what you have here, this right here is an equivalent capacitance, or what we would write, you'll see in all the textbooks, C sub EQ, for an equivalent capacitance. And so the utility of this is in our circuit analysis, whether we're dealing with capacitors, and you'll soon learn this with resistors, is you need to reduce all or part of a circuit to equivalent capacitance or resistance in order to determine, what's the current flow here, what's the voltage breakdown going to be here, various things like that. And so here we're just doing it to conserve charge and energy. In this case, we're conserving charge, okay? And so we have this, in this case, Q would equal the equivalent capacitance that we just computed. And one way to write this, we have equivalent capacitance for parallel would always be the sum from the first one to the last one of those individual capacitances. Capacitances. All right. So there we have our parallel capacitance function. And what's interesting, capacitors add arithmetically in parallel, but resistors add arithmetically in series. And they have a identical mathematical structures, but swapped. All right, so that's the parallel circuit has this feature. So let's do a series one, because that's the only other option besides mixing them. So a series capacitance, well, we could have a battery. We'll put it up top. And we'll put those same 3 capacitors in line. So again, plus minus on your voltage. We have C1, C2, C3. And here, we don't necessarily have the same voltage on each capacitor. The only way that the voltage would be the same on each capacitor is if each capacitor was the same capacitance. But whether it's capacitors or resistors, they will chew up some portion of the total voltage when they're in a series arrangement. Okay? So one analogy is you could think of a water park. You could just go one huge slide top to bottom, and you're going to pick up a lot of speed at the bottom. All right? Or you could have a tube that, you know, speeds you up and slows you down, you know, and those things would change your potential if you got a high, big drop, little drop, little drop, big drop. You know, you could change the way that it plays out. But you will go through the entire potential, but maybe not all at once. Maybe in different sized chunks. Same basic idea. So here we'll pretend they're all the same capacitance. But what will happen is, since there's one path for current flow, we're going to come back to this when we keep digging into circuit analysis after spring break, but we had one voltage. There's always one voltage in a parallel network with multiple paths for current flow, which means you could have multiple current values. Here, there's one and only one current value. Current must be the same everywhere in this circuit, regardless of capacitance. And if the current flow, meaning the number of coulombs per second, or the number of charge carriers passing a point per second, is a constant, then that means that the charge distribution on these plates, the charge on all of these plates is the same. Because there's only one current value. Because there's only one path for current flow. So now we're not dealing with the sum of charges. Now we need to deal with the sum of voltages, because that's what is getting divvied up here. All right? So I'll have a change in voltage for 1, plus a change in voltage for 2, plus a change in voltage for 3. Which means, so remember, capacitance was charge per unit voltage, which means voltage is going to be Q per C. So now I have Q1 per C1 plus Q2 per C2 plus Q3 per C3. But, just like we said before, Q1, Q2, and Q3 have to be the same. So what I really have is delta V is Q. So I guess we should write, you know, and one reason why is you have, let me back up here, your net charge in the middle here, those are 0. Both of those happen to be 0 there. So you just really have one capacitor in one sense. You have the stuff that's over here and the stuff that's over there. You have one charge distribution when it comes down to it. So there's two ways to look at it. The way I first described it, and then the fact that the net just leaves you with two plates, two opposite plates effectively. All right? So I just have Q. There's just one common charge on every plate, and it wouldn't matter what the capacitance is, all right, because of current flow. So Q, and then I'm going to have a 1 over C1 plus 1 over C2 plus 1 over C3. Now this could be 2 capacitors or 20 capacitors. It doesn't matter. This pattern is what you would follow. And so basically, once again, this is our equivalent capacitance, all right? And so we get Q over that equivalent capacitance. And mathematically, 1 over the equivalent capacitance is always going to be the sum from the first one to the last one of the 1 over those capacitances. Now it's easy when it's just 2, because then it's the product over the sum, if you want the equivalent capacitance. But when it's 3 or more, it gets fun. All right? That's why God invented computers. Let them do the heavy work for you. All right, so let's apply this to some. So let's have an example here. So step A is going to be a circuit with a bunch of series and parallel capacitors. And we're going to reduce the circuit down to something manageable. So we could have these 3 capacitors, C1, C2, and C3, and they could be parallel to C5 and in series with C4. And all of this parallel to some voltage. Let's have the circuit. Now, immediately, I can look at this and say, you know what? I can take this parallel network, and I'm using network for a reason because that's the jargon that goes with this game called circuit analysis. I have a parallel network embedded in a larger circuit. So circuits are a network, and they're comprised of sub-networks, if you will. But I'm not using network in the same sense as, say, like a computer network. All right? Maybe just network. So I could reduce this here, and so I could say that, you know what, C1, 2, 3, the equivalent resistance, would just be the sum of C1, C2, and C3. Well, that means in my next step, circuit B, instead of having those 3 in parallel, I could have the equivalent that I just computed, C1, 2, 3, and that is parallel to C5 in series with C4, and then all of that's still on the battery. So the circuit got smaller really quick by reducing a parallel network into a single one. But before I can deal with C1, 2, 3, and C4 in parallel with 5, I need to deal with C1, 2, 3 as a series. And the series formula that we just worked out says that C1, 2, 3, 4, or actually 1 over C1, 2, 3, 4 will be the sum of C1, 2, 3 plus 1 over C4. And so what that ends up being is a product to sum. So hopefully you can see that the common denominator would be the product of the denominators. And that 1 over C1, 2, 3, 4 would be C4 plus C1, 2, 3 over the product. And then if you flip it all over, you get the product over the sum. So we have C1, 2, 3 times C4 over the sum. So that means circuit C could be written as the equivalent resistance now, C1, 2, 3, 4, in parallel with C5, and all of that, parallel to the battery. So, again, parallel sequence, that's the easy one, you just add them. Okay, so now I can reduce this portion because it's ready for the game. So C1, 2, 3, 4, 5, which is going to be the equivalent capacitance of the whole network because it includes all the capacitors, will just be C1, 2, 3, 4 plus C5 because they're in parallel with one another. And so how will this work out? So C1, let me continue here, give myself some room. So C1, 2, 3, 4 was this C1, 2, 3 times C4 and then plus a C5. But C1, 2, 3 was C1 plus C2 plus C3 times the C4. And then it's just the sum of 1 through 4 in the bottom, and then a C5. Now we could perhaps try to get another common denominator and rigmarole around it, and that could be fun for the whole family. I'm not going to bother with that. But let's just say, let C sub I equal 5 nanofarads. So if every one of these things is 5 whatever, nanofarads, microfarads, whatever it ends up being. So I have 15 times 5 in the numerator, 20 in the denominator, and then I add 5 again. And so what would happen is you'd end up getting 8.75 nanofarads. Okay? Which is a little bit more than 5. One of the things about if it was just a parallel branch, whether it's, for capacitors in series, since it's that 1 over, your capacitance in series would never be larger than your smallest capacitor. And you'll find for resistors in parallel have the 1 over property, and so your resistance in a parallel network is never bigger than your smallest resistor in that network. And so we have these...
CI. That's CI equals 5 nanofarads, right?
Correct.
So each C1, C2, it's all...
If they're all 5, then it works out. But if they were different, we would just have some different... it would be a different number, obviously, if they were not all 5s. So that's just kind of a super basic... is the capacitance of one of them. Right, right. Then there's a little bit more we could do with this. I'm gonna get a clean screen. C1, 2, 3, 4, and C5 are parallel to one another and have, let's just say, 12 volts across them. So let's just let V equal 12 volts. All right? So what that would mean is that the charge on 5, since it's at 1 voltage, so I can immediately find out what's the charge on that single capacitor Q5, which you still have on your paper, but it's not on screen anymore, would just be equal to the capacitance of 5 times that voltage, which is on 5, which happens to be 12 volts. All right? In this case. So that means that our charge in this case would be the 5 nanofarads times the 12 volts, and that means I get 60 nanocoulombs of charge on that capacitor. So we're going for the easy kill in this case, because it was a single capacitor, and I know what voltage it's under, and I know what its capacitance is, which means I know how much charge is there. Okay, so we're accounting for charge today, largely. So there's that little modeling factoid. But C1, 2, 3, 4 is composed of C1, 2, 3, and C4 in series, which means both have the same charge. So this is going back to our analysis that preceded the example. How we're going to use those things that we deduced. They have all the same charge, which in this case would be what's on Q4. So the change in voltage here, or the difference in potential, is going to be the potential that's on 1, 2, 3, plus the potential that's on 4, which is going to be Q4 over C1, 2, 3, plus Q4 over C4, which will be Q4 times 1 over C1, 2, 3, plus 1 over C4. So Q4 would be our voltage, which is going to end up being 12, but we'll get to that in a minute. Would be this product of something that we computed, or we symbolized earlier. All right? And that means our delta V times the sum of all of those things that we saw before. So that means Q4 would be 12. The sum of those three, if they're all 5s, would be 15 nanofarads. C4 is another 5 nanofarads, so I got nanofarads squared over 20 nanofarads in that denominator. That means I'll work out with 45 nanocoulombs is what charge 4 is. Well, if capacitor 4, which is a single capacitor, has 45 nanocoulombs on it, and that same number of nanocoulombs is on the network for C123, which consists of 3, then each one of those capacitors has a third of the 45. So C123 consists of C1 through 3 in parallel, which implies Q1 equals Q2 equals Q3 equals 45 nanocoulombs over 3, which is just 15 nanocoulombs on those. So under the assumption of some given voltage, which could be anything, we could then, based on the known capacitance of each capacitor, how it's situated in a series or parallel or combined series parallel network, work backwards and determine where is the charge at any point in the circuit. All right? And so since there's multiple branches, we're going to have multiple current flows, which means multiple charges. Okay? But certain places will have a common charge, and other places will have an uncommon charge, if you will. So that's how some of that gets applied. We mentioned lightning a few times, so let's talk about thunderclouds. All right. So a thundercloud is 2 kilometers by 3 kilometers. I'm going to get rid of the yelling capitals there. Thundercloud, 2 kilometers by 3 kilometers, hovering 500 meters above flat water. It has a total charge of 160 coulombs. And that's flat ground, not flat water. I'm thinking of something else. And the ground has no charge. So that's our situation. All right. So, question A. What is the difference in potential between the cloud and the ground? Okay. So, first, this system is approximately a parallel plate capacitor. And the reason that it's approximately a parallel plate capacitor is because the opposite plate doesn't have any charge. Normally, a capacitor, one plate's plus and one plate's minus. But now the cloud plate is plus and the ground plate is nothing. So we're going to have to, if we're going to apply that model, which is the closest fit, okay, to this, we're going to have to think it through. So basically, the charge difference, delta Q, is going to equal 2Q because we have plus Q normally on a plate above and a minus Q below normally, which implies a difference of 2Q. Q minus a negative Q would be 2Q. All right? So this is subtle, but necessary. So for now, press the I believe button. Think about it later. And so let's get at the math here. So I have capacitance, which is supposedly defined as area per separation distance epsilon naught, which it definitely is. So that means I'm going to have an area of 2,000 meters times 3,000 meters per a distance of 500 meters times epsilon naught, which is 8.85 times 10 to the minus 12 farads per meter. And so we get a capacitance for this cloud ground capacitor of a whopping 0.11 microfarads. Okay? And so now I can rearrange the capacitance equation. And remember, and I guess this is a simpler way to think of this capacitor, if I have a total charge of 160 and I have a plus Q and a minus Q, that means I have 80 on one and 80 on the other. Perhaps that's a simpler way to think through the model, okay? But I like having multiple modes of thought. So 80 nanocoulombs of charge, and what did we, 0.11 microfarads, so I have a 10 to the minus 9th over a 10 to the minus 6th. And so we end up with 7.3 times 10 to the 8 volts. 730 megavolts. Okay? That's a lot of volts. All right? For a relatively, seemingly small capacitance, has a huge potential difference. Okay? And the breakdown voltage for air is 3 million volts. So this is At least I'm pretty sure it's 3 million volts. So what we need to find out now is lightning. I may be wrong about that. If lightning, yeah, I think I am wrong. If lightning requires 2.5 megavolts per meter, is there enough for lightning? That's supposed to be lightning. Guess all. That's why they don't let me teach English. All right, lightning. Okay, there we go. All right, so we do the math. So our electric field, I can, instead of V equals ED, I can just rearrange that to E equals that difference in potential per distance. So I have my 7.3 times 10 to the 8 volts divided by the 500 meters, that vertical distance. And this only works out to 1.5 megavolts per meter. So not enough. Need more charge to get there, or a bigger voltage rather. So no lightning in this case, but we were able to model a cloud, a thundercloud, as a capacitor, and know whether or not lightning was an issue. So my hunch is that this is something that meteorologists could determine, and therefore know, issue weather alerts, you know, be aware of various things. Yes, for the meteorologist. All right. One more about this. Part C, if you will. And this is where we hit the topic of electric potential energy. What is the electric potential energy? Well, I haven't given the formula, but I'm going to right now. Electric potential energy, well, I haven't given this version of the formula, is 1/2 Q delta V. New formula. You can look up in your book how it's developed. It's one of the simpler integrals, so I'm not going to bother with it. So 1/2 the charge, 80 coulombs, times that difference of potential we just found, volts, and so I get an electric potential of 2.9 times 10 to the 10th joules. Now, first, we don't normally deal with energy in terms of joules. We don't even normally deal with the units of energy in everyday life. So what is having 10 billion-ish joules, what does that compare to? That's a great question. Glad you asked. So let's take a 1,500 watt hair dryer, because I know that all of you are fashion-minded people and take great lengths to prepare your hair every day for school. And you blow dry it and all that jazz, especially chicks. So all I want to do is I want to convert this energy that I've determined is in this cloud, electric potential energy, and I want to convert it basically to watts to figure out how many hours this thing can go. So a joule, so this is the number of joules I have in the cloud. A watt is the number of joules per second. So I'm dealing with, if I want to compare the energy in the cloud to the power capacity of a 1,500 watt hairdryer, then I'm going to have 1,500 joules per second. So just to be clear, 1,500 watts, that's what this is. All right? Well, the joules will cancel, And so that'll be a large number of seconds. So instead of dealing with seconds, let's deal with hours. And there are 3,600 seconds in an hour. And again, my seconds will drop out. And so if I go through all of this math, this is going to equate to 5,370.4 hours. So the electric potential energy of this thundercloud, this 2 kilometer by 3 kilometer thundercloud, could run a typical hairdryer, a fashion-conscious hairdryer, for 5,370 hours. Which, how many days is that? 224 days. Okay? So that's how do you put these things in perspective? You just find the power consumption of something every day that you're familiar with and go, okay, that cloud, if I could convert that energy, I could run this thing for, what, 3/4 of a year, whatever that is. Okay, so that's a lot. Okay? But let's deal with another example. So let's say we need to store, for some crazy reason, 95.6 joules on a bank of parallel capacitors, each with a capacitance equal to 90 microfarads. Under a voltage of 160 volts. How many capacitors will it take? All right, so that's our problem. So let's draw a circuit, since it asked us to deal with a circuit. So here's my voltage, and I'll have capacitor 1, and then I'll have capacitor 2, and this will continue for a while until I get to capacitor N, whatever that is. And the equivalent resistance of this parallel thing will just be, because they are in parallel, you just add. So that this is our model, all right? And the reason I did this problem, it's a simple problem, but I also wanted to introduce, there's a variation of the potential energy equation, and it's 1/2 C times delta V squared, which is just substituting in the capacitance equation and getting a different version of the same thing. So I wanted to bring those two out. And in our case, it's going to be the equivalent resistance of that. And the equivalent resistance is just going to be equal to this number of capacitors that we're interested in times the capacitance, if they're all the same, right? There's going to be n capacitors of this capacitance, so the equivalent, since we're just adding, is just going to be NC. There's no formula for that. You have to just reason it out proportionally, all right? So that's NC. So then we're going to have 1/2 N times that capacitance, which is this one, times the voltage squared. So let's be clear here. We have 95.6 joules. That's what the U is. We have a voltage of 160. That's what the delta V is. And we just worked out NC. And we want to solve for N. So N will equal double the potential over the capacitance voltage squared. So 2 times 95.6 joules over 90 microfarads and 160 volts squared. And that will work out to roughly, it's actually 82.9 something, so 83. Can't have, 98% of a capacitor. You need to have the whole capacitor. So roughly 83 capacitors. Okay, why would we do this? We were out of, whatever the sum of that is. 83 times 90 is capacitors, but we had 83 of these laying around, so we're going to use these. So it's just some design limitation requires that we use that. Now, this isn't likely in reality, but having a constraint like that is guaranteed. You're guaranteed to have a constraint that forces you to do something like this in real life. Doubtful it would be this, okay? But it would be something like this, where you're like, I only have this available. Or for some other reason, I can only use this component that has some property or set of properties. Then you have to configure them in a way that achieves your goal. Maybe it's the case that for some reason, I can line up 83 of these because they're really small as opposed to one larger one. Or maybe these ones have the capacity to be waterproof, whereas the other one doesn't. There's an infinite number, well, maybe not infinite, but there's a lot of variations that would force you into a box like this. Like this. Right? So that's so let's do a little dielectric. Gauss. All right, stuff. Sorry for the high-tech terminology. So first, in a vacuum, where my Gaussian surface only includes surface charges. Meaning surface charges on some capacitor plate. So here's I need to make that bigger. So here are these plates. So there's a vacuum in between there, and my Gaussian surface would only include surface charges on the actual capacitor. We're going to slide dielectrics in there, and then my Gaussian surface would include surface charges and charges in the dielectric volume. Okay, so that's where we're headed. Just so a warning there. All right. So, by the way, we can put that epsilon naught out in front of our line integral. I haven't shown it that way before. But this is sort of old news. The reason why we can do that is because it's equal to Q per epsilon naught, so I can just move the epsilon naught as a constant. All right, so it's just a different way to pitch it. And so this means that my initial electric field without a dielectric would be exactly what I expect it to be, A epsilon naught. So we have that. That's a review. We've done this already. What about or I shouldn't say in a dielectric, with a dielectric. Boy, I'm in spelling problems today. With a dielectric, and so now that means that I'm going to have in my Gaussian surface charges and dielectric charges. Okay? So what is that going to work out to be? Well, still the case that I'll have Gauss's law the same as it always is. It always is this line integral of EdA, which is going to give me an EA, but now I have the Q that I had before, the big Q that was on the surface things, minus some other Q in the dielectric. Okay? So I have the Q that I had before initially, but now, so up here, I have Q here, and I have little q there. So I have a difference of charge when the Gaussian surface includes the dielectric material, which it needs to. We're going to deal with the dielectric in Gaussian terms. All right? And so what this gets us to, well, first, realize that our E would then work out to be Q, big Q minus little q over epsilon naught alpha. So it's just rewriting the standard issue. It's got to be some amount of charge per epsilon A. And in this case, that some amount of charge is the difference of the big Q and little q. All right. Nothing really changed here except the way we symbolize it by necessity. And so this happens to equal, this is going back a few pages in your notes. Remember what we developed from the Faraday viewpoint? That this would be your initial capacitance, meaning the one before we slid dielectric material between the plates. All right? Because that dielectric material is now weakening the electric field by that factor kappa. All right, so it was earlier in the lecture. So we can continue here. This is going to get me Q per K epsilon naught area. So now I'm going to continue right here. This means I'm going to have Q minus little q per epsilon naught alpha equals Q per K epsilon naught. I keep saying alpha and it's A. Sorry for that. And then this, okay, is going to give me Q minus little q equals big Q per kappa. We're not done. Okay, we got some things to do. So the if it's the case, and it is, So we'll just bring this down here. So epsilon naught EDA is going to equal this Q minus Q, which we just figured out is Q per kappa. This means that I can just literally bring that kappa into Gauss's law. So this kappa, I'm sort of out of room here. I can write it as epsilon naught integral of kappa electric field dot dA, and that has to equal Q. So this is the Gaussian form for dielectrics. So for a parallel plate capacitor. So it sneaks in. Of course, we could probably put it out with the epsilon naught as well. It really wouldn't matter much. But it's associated with the diminished electric field, also with the other one. So that is a wrap. I didn't think I'd get through it all today, but we did.